Okay, so today we're going to start talking about Newton's 3 laws of motion. And you say, well, why are we talking about laws of motion, Dr. Davis? You just told us in the last video that this class is all about statics. So basically we're talking about stuff that aren't moving. Why are we dealing with laws of motion? Hopefully that'll be a little more clear as we progress through this. All right, so let's just review from physics for a second. What's the first of Newton's law, right? We sometimes say it this way. If a body is at rest, it stays at rest. And by the same token, if a body is in motion, it stays in the same motion. But there's kind of a except, right? Except when acted on by a force, right? So here's Newton's first law. There's another way of stating this, right? What this is if the sum of forces on a body equals 0, right? Then the time rate of change of velocity equals 0. Equals 0. So the other way of writing this is that here's the sum of all the forces acting on a body equals 0. And that means that the time rate of change of velocity, which by the way is also a vector with respect to t, equals 0. So there's Newton's first law. Let's talk for just a second about Newton's second law. So we have a tendency to just say, hey, Newton's second law is F equals ma, right? So let's just write it. F equals ma. But we have to recognize what we're really talking about is the sum. The sum, again, of those forces acting on a body equals the mass of the body times acceleration. Or, by the way, that's the mass of the body times dv dt, right? This is nothing more than acceleration, okay? So there's a nice compact equation that describes the relationship between acceleration and force. Then we have Newton's third law, and Newton's third law is often kind of represented as sort of equal and opposite, right? Equal and opposite forces. So what we're saying is that all the forces that body A is applying to body B is equal to all the forces that body A is applying to body B, but opposite in direction, right? So there's the 3 laws. This is all for linear motion. There's some equivalent laws for angular motion. So for angular motion, we're going to talk about angular momentum, right? So here what we're going to talk about is the time rate of change of angular momentum. So we're going to call angular momentum L. So the time rate of change of angular momentum is equal to 0 when the sum of torques, sum of the torques on the body equals 0. Or we can actually write Newton's second law sort of in an angular motion reference. We can say that the sum of torques on a body equals dl dt. All right, so I'm going to expand what dl is. dl is the moment of inertia of the body times the angular velocity. The moment of inertia of a body is a property of the body. It doesn't change with time. So we can write that as I times d omega dt, right? So this is an omega here. By the way, both of these are vectors as well. Sorry about that. All right, so this is moment of inertia, a property of the body, times d omega dt. This is basically equivalent to this dv dt, okay? So now let's think for a second. If we're dealing with statics, I told you that that's a body that's not accelerating, right? So what did I tell you earlier? In the previous class, previous video, I said all we're going to mess with in this class are things where dv dt equals 0, right? And if we're talking about something spinning, then equivalently, we're only going to deal with things where d omega dt equals 0, right? So this is all we're going to deal with in this class. And I'm going to leave a little extra space. Because if we go back, whoops, need a straight edge. If we go back and look right here, we recognize that if dv dt equals 0, then sum of forces equals 0. So all we're going to deal with is this, the sum of forces equal to 0. If d omega dt equals 0, then the torque, the sum of the torques equals 0. Oops, didn't quite draw a good summation sign. Hopefully you get the point. So there they are. We've just derived the only two equations that really matter in this class. The sum of forces equal to 0 and the sum of torques equal to 0. We'll actually learn at the beginning of this class, for many cases, we don't even have to worry about this. We just have to worry about this one single equation. Again, the trick is learning to apply them in a wide range of situations, and that's where the exercises will come in.